Okay, hi everyone, welcome back to this video series on the Comptia Security Plus course PGP. Pretty Good Privacy is an encryption program used primarily for signing, encrypting and decrypting emails in an attempt to increase the security of email communications. You might remember that we previously discussed weakness of email client programs when sending via POP3 and SMTP servers. PGP users actually wrote the encryption specification as shown in the Open PGP standard. Other similar programs use this as well. Today, PGP has an entire suite of tools that can encrypt email, accomplish whole disk encryption, and encrypt zip files and instant messages. PGP uses a symmetric key session, also referred to as pre-shared key or PSK, and as much. You might hear PGP referred to as a program that uses symmetric encryption, but it also uses asymmetric RSA for digital signatures and for sending the session key. Because of this, it is known as a hybrid crypto system, combining the best of conventional systems and public key cryptography. When encrypting data, PGP uses key sizes of at least 128 bits. Newer versions allow for RSA or DSA key sizes ranging from 512 bits to 2048 bits. The larger the key, the more secure the encryption is, but the longer it takes to generate the keys, although this is done only once when establishing a connection with another user. The program uses a combination of hashing, data compression, symmetric key cryptography, and public key cryptography. Newer versions of the program are not fully compatible with older versions because the older versions cannot decrypt the data that was generated by a newer version. This is one of the issues when using PGP. Users must be sure to work with the same version. Newer versions of PGP support Open PGP and SIME, which allows for secure communications with just about everyone because it works with RSA. The security of PGP is based on the key size. It is considered secure and uncrackable as long as a sufficient key size is used. As an example, it has been suggested that a 2048-bit key should be safe against the strongest and well-funded adversaries, with knowledgeable people and with the latest supercomputers until at least the year 2020. 1024-bit keys are considered strong enough for all but most the sensitive data environments. Around the turn of the millennium, the creator of PGP and many other security-minded people that used PGP sensed that an open source alternative would be beneficial to the cryptographic community. This was presented to and accepted by the IETF, and a new standard called Open PGP was developed. With this open source code, others could write software that could easily integrate with PGP or replace it. One example of this is the GNU Privacy Guard, GPG or GNUPG, which is compliant with Open PGP standard. Over time, this has been developed for several platforms including Linux GUIs, Mac OS, OS X and Windows. GPG in a combination of symmetric key encryption and public key encryption. PGP and its derivatives are used by many businesses and individuals worldwide so that files can be easily encrypted before transit. The original PGP, developed by Philip Zimmermann, has changed hands several times, and so of this writing is owned by Symantec, which offers it as part of its products for free. There are also several versions of PGP as well as GNUPG available for download for free. A good starting point is following the link http://openpgp.org. Pseudorandom number generators. The pseudo-random number generator (PRNG) is used by cryptographic applications that require unpredictable output. They are primarily coded in C or Java and are developed within a cryptographic application such as a key generator program. Within that program there is a specific utility, for example SHA-2PRNG, that is used to create the PRNG. Remember to use SHA-256 as of the writing of this book or higher. For additional randomness, a programmer will increase entropy, often by collecting system noise. One of the threats to PNGs is the random number generator attack, which exploits weakness in the code. This can be prevented by implementing randomness using AES, using newer versions of SHA, and maintaining physical control of the system where the PRNG is developed and stored. Hashing basics. A hash is a summary of a file or message, often in numeric format. Hashes are used in digital signatures, in file and message authentication, and as a way to protect the integrity of sensitive data. For example, data entered into databases or perhaps entire hard drives. A hash is generated through the use of a hash function to verify the integrity of the file or message, most commonly after transit over a network. A hash function is a mathematical procedure that converts a variable sized amount of data into a smaller block of data. The hash function is designed to take an arbitrary data block from a file or message, use that as an input, and from that block produce a fixed length hash value. Basically, the hash is created at the source and is recalculated and compared with the original hash and the destination. Figure 4.2 illustrates this process. Note that the hash that was created starting with CE114E and so on. This is the summary or message digest of the file to be sent. It is an actual representation of an MD5 hash covered shortly of a plain text file with the words "This is a test" as shown in the message portion of figure 14.2. Because the hash is a condensed version of a file, message, or a portion of it, it is also known as a message digest. It provides integrity to data so that the user knows that the message is intact, hasn't been modified during transit, and comes from the source that the user expects. A hash can fall into category of one-way function. This means it's easy to compute when generated, but difficult or impossible to compute in reserve. In the case of a hash, a condensed version of the message, initial computation is relatively easy compared to other algorithms, but the original message should not be recreated from the hash. Contrast this concept to encryption methods that indeed can be reversed. A hash can be created without the use of an algorithm, but generally the ones used in the field require some kind of cryptographic algorithm. Cryptographic hash functions. Cryptographic hash functions are hash functions based on block ciphers. The methods used resemble that of cipher modes used in encryption. Examples of cryptographic hash functions include MD5 and SHA. Let's discuss a few types of hash functions now. MD5, the message digest algorithm. MD5 is the newest of a series of algorithms designed by Ron Rivest. It uses a 128-bit key. This is a widely used hashing algorithm. At some point you have probably seen MD5 hashes when downloading files. This is an example of the attempt at providing integrity by checking the hash produced by the downloaded file against the original hash, you can verify the file's integrity with a level of certainty. However, MD5 hashes are susceptible to collisions. A collision occurs when two different files end up using the same hash. Due to this low collision resistance, MD5 is considered to be harmful today. MD5 is also vulnerable to threats such as rainbow tables and pre-image attacks. The best solution to protect against these attacks is to use a stronger type of hashing function such as SHA-2 or higher. SHA, the secure hash algorithm, is one of the number of hash functions designed by the US National Security Agency NSA and published by NIST. They are used widely in the US government. SHA-1 is no longer considered to be secure because there is the potential for successful collision-based attacks. It employs a 126-bit hash and as of 2017 has been deprecated. Any websites or other applications using SHA-1 are required to be updated to a higher level of SHA or other hashing algorithms. SHA-2 is more secure. It has a 256-bit and 512-bit block sizes, plus truncated derivatives of each. KCAC was selected from a group of algorithms in 2012 and SHA-3 winner, but is not meant as a replacement for SHA-2 because no compromise of SHA-2 has yet been demonstrated. It is important that a hashing algorithm be collision resistant if it has the capability to avoid the same output from two guessed inputs by an attacker attempting a collision attack. It is collision resistant. When it comes to cryptography, perfect hashing is not possible because usually unknowns are involved, such as the data to be used to create the hash and what hash values have been created in the past. Though perfect is not possible, it is possible to increase collision resistance by using a more powerful hashing algorithm because MD5 and SH1 have vulnerabilities. Some government agencies started using SHA-2 as early as 2011 and most likely will use SHA-3 at some point. For added security, a software key computed with either SHA or MD5 might be compared to a hardware key. Some software activations require this. In fact, if the hardware and software hashes values don't match, then the software won't activate. Or RIPEMD and HMAC. RIPEMD stands for Race Integrity Primitives Evaluation Message Digest. The original RIPEMD 128-bit had a collision reported, and therefore it is recommended to use RIPEMD 160-bit, RIPEMD 256 or RIPEMD 320. The commonly used RIPEMD 160 is a 168-bit message digest algorithm used in cryptographic hashing. It is used less commonly than SHA and was designed as an open source hashing algorithm. HMAC stands for Hash-Based Message Authentication Code. Let's step back for a moment. Message Authentication Code, MAC. MEC is a short piece of information, a small algorithm used to authenticate message and to provide integrity and authenticity assurance on the message. It checks the integrity of the cipher used and notifies the receiver if there were any modifications to the encrypted data. This way, the data cannot be denied, repudiated when received. Building on this concept, HMAC is a calculation of a MAC through the use of cryptographic hash function such as MD5 or SHA-1. If, for example, SHA-1 is used, the corresponding MAC would be known as HMAC SHA-1, or better yet, if using SHA-2, due to SHA1 deprecation, then you would probably use HMAC SHA256 or higher. Warning, be very careful selecting the type and version of hash function that you use. LANMAN, LTM and LTM version 2. Passwords can be hashed using algorithms. Some password hashes are more secure than others, whereas older ones have been cracked and are therefore compromised. This section details the Windows-based LANMAN, NTLM and NTLM v2 hashes starting from the oldest. These three types of authentication are what attempts to make your login to the Windows computer secure, unless you log into a domain where Kerberos is used by default. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.